So we want to draw the root locus for this. And the system here, the root locus, is based on the GH. And this is G here, and H is equal 1. And so, what is the first step in drawing the root locus? Put down the poles and zeros, put where k equals 0, where k equals infinity, and wherever you can on the real axis, draw in the root locus. Okay, so anybody want to try to do it? I can kind of guide you through it if you need help. So we have a 0 at -2, so if this is -1, this is -2, we have a 0. And then we have complex conjugate poles, right? And I put it in this form. You could write it as s squared plus 2s plus 3, right? That's just multiplying it out. But if you put it in this form, what you can see is that the roots are automatically going to be -1 plus or minus j square root of 2. Okay. And so we put here's -1 j square root of 2. Here's so 1.4. So j square root of 2. And then we have a pole there and a pole there minus j square root of 2. Does anybody want to try to complete this root locus? Any volunteers? Come on, you guys. No? So where does root locus exist on the real axis?
To the left of the 0.
To the left of the 0, right? Take a test point here. That test point is to the left of an odd number of poles or zeros. So it exists here and is directed towards what?
0.
It's always directed towards a 0. So close up, you can put that. And also, what is the value of the gain k at the open loop transfer function poles? 0.
Infinity.
Infinity. And so you label that as well. And here k is equal to 0. And k equals 0. So, and how many asymptotes does this have? It's 1, right? It's a difference between the number of finite poles and finite zeros. So it's 1 asymptote. And when there's 1 asymptote, that is always going to point or go along the negative real axis, right? And so we can put that in, right? Actually, we really don't need to put in the asymptote because it's normally indicated as a dashed line, and here you can't really draw it on top of that. So it is going to terminate, the root locus is going to terminate at the open loop transfer function zeros, 1 finite and 1 where? Minus infinity, right down here. Right, so we can kind of break the axis, we call that minus infinity there, and that's where k equals infinity. Okay, so the root locus begins at the open loop transfer function poles, and by begin, that means k equals 0. And they have to end, the root locus branches have to end at the open loop transfer function zeros. So what do you expect that this the branches will do here? Yeah, right? Do what? Go around, right? And enter the real axis somewhere. Okay. And so I'll put it in like this. And roots always in complex conjugate pairs, right? If they're complex, they're in pairs. And so it's going to be a mirror image about that, the real axis. And so then we put down the direction. It's always directed away from poles, right? So we can say that we can put that arrow like towards the open loop transfer function zeros.
Just a quick question. Is it typically going to have a sort of circular shape around a zero? Is that what it's going to look like when you sketch it?
In cases like this,
Mhm.
or some other certain cases, here, for example, if you have two poles and the zero here, turns out that it's a circle.
Mhm.
Okay, I mean, we can't always describe every root locus as having a certain shape.
Right.
But in this case, right, it turns out to be a circle whose center
Just
is
around
that
that.
zero there.
Okay.
Okay, if you had these two poles instead there and there, if they were right there, you'd have a complete circle
Mhm.
whose radius is that distance from here to here or from here to here.
Okay.
Okay.
So in that case, could you sort of calculate where they're going to be meeting back on the real axis by finding the hypotenuse distance between the zero and one of those poles?
Yeah.
Mhm.
Yeah. Well, let's say if you know of course, if you know this distance, you
Mhm.
know that distance from
Yeah.
the circle.
Okay.
Right. But yeah, if you can determine if it turns out to be a circle, then
Mhm.
if you can determine any one point,
You can find out where it's going to meet back on the axis. Okay. All right.
and here, for example, it looks like this, right? And so if this is minus 1 and this is minus 3,
Mhm.
that distance in there is 2, so that distance has to be 2. Does that make sense?
Mhm.
And so it re-enters, it breaks away, and it re-enters at 2 minus 5. Okay. Also, you could have something like this. Say a pole here at -1, a pole there at 1, a 0 at minus let's see, this would be the breakaway point. So 1 minus 2, say -2, and let's say a 0 here and a 0 here. Right? It would do something like this in this case. Okay. Right. It would come together. The branches come approach each other, break away, re-enter. One branch towards that finite 0, the other branch towards that finite 0.
Mhm.
Back to this one. This is what the root locus is. How can we find this re-entry point, or it's actually an entry point?
Mhm.
Take the derivative of k. So first you have to find the expression for k. How do you find the expression for k? Start with the characteristic equation. That's what it's all based on, right? And the characteristic equation is 1 plus k s plus 2 over s squared plus 2s plus 3. So k is equal to 0. So k is equal to minus s squared plus 2s plus 3 over s plus 1. And so you do the dk ds for this, right? And dk by ds equals 0 results in this quadratic equation, s squared plus 4s plus 1 equals 0, right? Take the derivative of the quotient. This times the derivative of that minus that times the derivative of that.
Mhm.
Over that squared set equal to 0. So it doesn't matter the denominator. It's setting equal to 0, so it's
Mhm.
going to go away. So you have this quadratic equation here, and the roots are minus 2 plus and minus the square root of 3, which means that they are at minus 3 3.732 and minus 0.268. Okay, and so you can see, how do we use these? Just
One
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 each
different
time.
to the left of the zero, like on the root locus.
Say it again.
The negative 3.732 is on the root locus, the other one's not.
Yeah, this point down here is not on the root locus, right? Because this, what we had was this problem here, pole there. So we can't use that, and we do use that, and this is minus 3.732. And so this distance is the square root of 3. And so you have square root of 3. And that's the radius, and therefore this point minus 2 should be, this point here should be minus 2 plus
J square root of 3.
J square root of 3. Right.
Okay.
And so there's one other thing that we can find on this, that is the angle of departure of the root locus from the open loop transfer function pole. Right. In other words, this angle in here, if we draw that dash and the dash, then this is the theta d, the angle of departure. That might be useful information. It says, okay, it's not coming away like that, it's coming away like that. Okay, and actually that we can determine that, right? How do we determine how do we determine the angle of departure?
Do we need a Rockaway? A Rocko array?
No,
Is it the
well, there is the angle condition, right? Angle condition. So let's draw it in a little more, a little bit larger, say, and put in the angles of interest, right? Remember, in applying the angle condition, you draw a vector from each of the poles and zeros to the test point. Okay, and so what we'll do is we have this pole here at where is that pole? This pole is at -1 plus j square root of 2, right? And this is the supposed root locus, a branch of the root locus, okay? And so what we'll do is, and that's a pole, we have a 0 also at -2, so here we have a 0 at -2. And remember, there's a pole down here as well, right? So that minus j square root of 2. And so we can take, what we'll do is, let me redraw this like this. And what we'll do is take a point on the supposed root locus, a branch of the root locus, and draw a vector from each of the poles and zeros to that test point, or that point. But in the meantime, we can also see, draw a vector from the origin to that test point, from that pole to the test point, from here, from here, right? And so we have these angles. I call this phi prime. I call this angle here. Remember, the angles are always measured relative to the positive real axis. And so this angle, I called it theta d prime. See, it's not the angle of departure, because the angle of departure occurs right at the pole. You see, I drew a tangent right at the pole there. And this one, I'm just drawing a vector from the pole to a test point on the real axis. Okay, but if you take the limit, and then let me call this vector here epsilon. the length of that vector. If you take the limit as epsilon goes to zero of theta d prime, you get theta d, which is a desired angle. Okay, that's this angle here, theta d. Because this vector is getting smaller, 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 and so finally it's tangent there. Okay, yeah.
Are you saying the test point is moving, or is it just the vector itself is shrinking?
The vector itself is shrinking.
Mm.
So when the vector itself shrinks to zero,
Mm-hmm.
then that theta d prime becomes theta d.
Okay.
And that's what we want to find.
Mm-hmm.
So let's apply the angle condition to this test point here. Right? It's the sum of the zero angles minus the sum of the pole angles. Right? And so this pole angle, what do I call it? Theta prime. So I have a theta prime, a phi prime, and a theta d prime. And so now what I'm going to do is let epsilon go to zero. Okay, and when epsilon does go to zero, what we'll have then is minus j square root 2. We have j square root 2. We have minus 1, and we have that pole there, and that 0 there. This will have, this will become, see this is 54, that's going to be 54.7 degrees, right? In other words, the arctangent of square root 2 over 1, square root 2 over 1, okay? And this angle here is clearly 90 degrees, right? So in other words, when epsilon goes to 0, this angle phi prime becomes 54.7. This angle theta prime becomes a 90-degree angle, and the theta d prime just becomes theta d. Okay, so we can apply the angle criterion. We can say that first of all, we can say that phi prime minus theta prime minus theta d prime, right, is equal to plus or minus 180 degrees. That's sufficient, plus or minus 180. And so this is in terms of these angles here. So now when we let epsilon go to 0, the phi prime becomes 54.7 degrees minus the theta prime, which becomes 90 degrees, right? So I mean, we can take that, right, with the plus sign in there. So 90 plus theta d is equal to 180. Okay. You can use plus 180 or minus 180. Okay. And so this is the equation allows you to find theta d. Okay, so you have 54.7 minus 90 minus 180 is equal to theta d. Bring theta d to the other side. 54.7. Okay, so this is minus 270 plus 54. Or you could use minus here, and that becomes a plus there. So that becomes 90 plus 54.7. 9 and 5 is 14, right? So it's theta d is equal to 144.7 degrees. You can use it that way. You can do it that way too. Okay, so if you go back here, you see, I already knew kind of what theta d was, right? So, so I kind of put it in there. But now we can put it in there. This angle in here, theta d, is 144.7 degrees. And that just gives you a little bit more information about what the branches, how the branches are shaped or So that's one problem. We can do another problem here. Maybe somebody would volunteer. Any more questions about this? Anything I have missed? This branch is directed like that. Right? And I have my directions here and here. And so I think it's pretty complete. Okay, so let's erase this one. And we'll just put in a new one in here. Let's see, so it'll be KS plus 1 over S minus 1 quantity squared S plus 5. So we have that. And what we'd like to do is draw the root locus plot for that. Does anybody want to try that? Okay. Come on. Sure.
Oh, yeah, right.
Okay, go ahead. It's all yours.
No, it's ours.
So you just have to put down the poles and zeros, right? At this point, yeah. And in fact, there's a double pole at 1, right?
Sorry,
A plus 1. Yeah, double pole, so you put 2 X's. That's good. Yeah. What else can you do on the real axis?
I can draw those arrows, right?
Yeah. Yeah. Draw where it exists on the real axis. To the take test point here is to the right and left of how many?
It's to the right of this one.
No.
2 of them. Oh, okay. Yeah, there's 2 of them. So
Yeah.
the next one would have to be here.
Well, take a test point there. That is to the right of how many singularities?
That's 3 of them, so that's not a singularity, so I'm allowed to do that, right?
So you're allowed, yeah.
Anything here? Like that, right?
Yeah. And then by the 0, what can you do?
What do you mean?
I mean, just like you said, you know that the branch is always directed away from a pole,
Correct.
always directed towards
Right, so that's what.
towards a 0. Yeah. So I mean, it's good to put it up close there.
Okay.
Also. Next thing, you put down K, where K equals 0, where K equals infinity, right? Yeah. Now, what can you say about how many branches should this have?
3 minus 4, 2, 3, 2, 3, 1, so 2.
2.
Right, because there's 1 on top, 2 on the bottom. So 3 minus 1 is 2.
Yeah. And so how many? How many asymptotes.
There's an equation for that.
Uh,
So there's an equation for that.
It's just the difference between the order of the denominator and the order of the numerator.
Okay, so two.
It's two. Yeah, two asymptotes. Now, can you find the angle of the asymptote?
We should be able to do that. Yeah, using the theta equals 180 n over alpha, right?
Alpha, and alpha is equal to 2, right? The difference between the number of holes, finite holes and zero. Sorry, and plus or minus 90 degrees, right? And those are the only two unique angles, right? If you put n equals 3, you get 90 times 3 is 270. Plus or minus 270 is really the same as plus or minus 90. And then what else, after you find the angle of the asymptote, what can you do? Find something else about the asymptote.
Anybody want to help me?
You would find where it's actually at me solving for
Origin of the asymptote?
the formula is the zero location. No, pole locations minus the zero locations over alpha.
Pole location. Minus zero location. So that would be pole locations is 0 minus 0. I'm sorry. 1 minus 1.
It's 1 plus 1.
Yeah, 1 plus 1
Oh, yeah, okay.
minus the 0 locations. So I got the 5. Negative 5. And, 0 locations is going to be negative 1. So 2, negative 3, negative 2 over alpha, which alpha equals 2, so negative 1.
Yeah.
Okay. Right here. So that's where my asymptotes are going to be, positive asymptote
Absolutely.
and my negative asymptote.
Yeah.
Okay. And then I can like find my entry points and my entry exit points.
Well, look over here. You see these two poles there? The root locus begins there, right? And it terminates at the zeros, which are, in this case, there's the minus 1, but there's also two asymptotes. And so you can say that there are some branches that are directed towards those lines, towards those asymptotes. Right?
Those cross those asymptotes, or they just kind of branch off to make it positive? Is that how it's doing?
They go towards the asymptotes, towards plus and minus infinity.
So kind of like this.
Oh, like
and like this.
straight up and
Yeah.
straight down.
Okay, I think it's okay.
Yeah. In fact, I think actually we can find the angle of departure here in the same way that we did over there.
Okay.
It turns out that it's going to be 90 degrees.
Okay.
Okay. So instead of going like that, it's going to go like that. Right. But don't worry about that right now.
All right. So you just want me to draw that on there?
Draw that. Yeah.
So you're saying it's like an exit point up like this, and then it's going to kind of curve like that, and then go back up.
Yeah. It gets closer and closer.
And the same thing going this way.
All right. And now you can also put down the directions of the branches that you have there. Yeah. And so you have two asymptotes, one here, one there. these two branches approach the zeros at infinity. Right, we have 1, 0 at -1 plus j infinity, and the other one at -1 minus j infinity, right? So you could put in like that, like up here, k goes to infinity, and so the point will be -1 plus j infinity, terminates at the open loop transfer function 0. Oh, can you find the range of gain k for stability?
Range of gain k for stability. Should be able to do that.
So we only need to actually solve for k and take the derivative when there's a breakaway point?
But in this case, notice, this is the breakaway
No,
point.
yeah, I understand that, for this case it is. Okay,
Yeah.
that answered my question,
Oh, okay.
thank you.
Say that one more time, Professor. What do you want to find?
So find a range of gain k for stability.
For stability.
So we've done that before, right?
Yes, we
That's
have.
a what's it called? What test is that? Ralph test. Right? And for the Ralph test, what do you need to start with?
Characteristic equation.
Characteristic equation.
So this is the characteristic is going to be 1 plus k s plus 1 over s minus 1 squared times s plus 1.
Yeah. And so how do you proceed from there? If it's an equation, where do you have to
Set it equal to 0.
set it to 0, right? And so now you can
Solve for k.
no, because it's the characteristic equation that you want, right? That you want the characteristic polynomial actually, and you want the coefficients of the characteristic polynomial to form this array. Right?
So I'm finding the x's then? Is that what you're saying?
This is the one form of the characteristic equation. If you want to clear the denominator, you have to multiply through by that, right?
Correct.
So you just got that product plus k times that equals 0. That's your characteristic equation, right?
That's a question. About how many branches, how do you solve for?
You multiply also by the denominator on the top too, right? You, yeah, because you multiply by
Yeah. The
the bottom over the top. Or, I'm sorry.
number of branches
This is right?
is
Oh.
always equal to the order of the denominator.
Oh, wait, canceled it out. That's right. Okay. My fault.
Alright, so you multiply that all out, right? So you got this actually.
Multiply this out too.
Yeah, you'd have to multiply it out. Okay, you want to continue?
Want to write it up here so everybody can see it?
Yeah.
S, right?
Oh, there's something else.
Say it again, right, minus 9 is 10?
Yeah, that's -9.
Okay.
And,
Everything else is right? Is agreed?
K, you're missing the K.
Okay.
The constant. So it's gonna be K plus 5. Instead of 11, it's K plus 5.
K plus 5.
Okay, great. Now you want me to solve that?
No, you form the Rouse array, the Rouse table.
Oh, that's right, you gotta do the, look at this one and the S, right? So let's start with that, so we got 1. S squared. 0, right?
Yeah.
Okay, it's 9. What's for the S to the 0 one again?
Now you gotta form this. So multiply.
That 3, the 3s squared should be positive right now.
Yeah, that probably should be +3.
3s squared is positive, yeah. Plus 3. Yeah.
You get 3K minus K is 2K, right?
Say that one more time, Professor.
Go ahead.
Set this equal to greater than 0, right?
Yeah, but you simplify that first.
Find this first. So I can go ahead and say K minus 9 plus 5 over 3.
Yeah, or just remember that you can always multiply through by a positive number, right? So you just be dealing with that.
So that would be 3K minus 9 minus K minus 5.
Yeah. Right, so you got 3K minus K, that gives you 2K minus 18 minus 5. Oh, 3 times 7. So now you got 1.
2K minus 32.
Yeah. Okay. Yeah. Yeah, and then you divide by that, right? So it goes away. And so you just get K minus 5, and then plus 5. So get plus 5. Okay, so you look down here, right? No sign changes, right?
No sign changes.
Must have no sign changes. Therefore, this is greater than 0, greater than 0. This has to be greater than 0. That has to be greater than 0, right? So K has to be greater than what?
0. So it's going to be 32 over 2, so 16.
Yeah, K has to be greater than 16, right? And here you get K greater than minus 5. So out of these two, the mutual, what do you call it?
Greater than negative 5.
These two mean that K has to be greater than 16.
Correct.
So because K greater than minus 5 and K greater than 16, this one predominates.
Correct.
Okay, so what that means is that you can, at that point there, again, K is equal to what? 16. Right? It's going to oscillate when K is equal to 16, right? Then you can, if you wanted to, you could go back and find the auxiliary equation, 3s squared with K equal to 16, that gives you 21, right? And you've got the auxiliary equation.
S times S plus A or something like that, right?
Yeah, it's a 3s squared plus 21 with K equal to 16. And so you can find, set that equal to 0, right, and 24, s squared plus 7, right? So s equals plus and minus j square root of 7. And that's what s is equal to there. And so the range you gain k for stability is what?
The range you gave is going to be from k is greater than -5, but you said that the k is greater than greater than 16 is more predominant.
Yeah, that's it. Okay. That was very good.
Good job, Professor.
All yours.
Thank you.
Okay, so we did that problem, and what I'd like to do is just show a bunch of root locus plots that I did the root locus using MATLAB for several of these here, which is on page 289 of the textbook. So what I want to do is just go through those and show various features or whatever about them. Show you that it's really easy to do it with MATLAB, and the thing is that we want to be able to look at these MATLAB root locus plots produced by MATLAB and make sense out of them. That's why we want to go in detail through the graphical root locus construction rules. Anybody needs their exam, actually, it's up here. So, second. First of all, I wanted to show this here. That is these are various root locus plots, and we could just take a look at these, or we could take a look at the MATLAB code as well. But here, for example, what you start out with is 3 poles. There are no zeros there, right? So you can put down where the root locus exists on the real axis, right? Between there and there, all the way out to minus infinity. And then also you can find the number of asymptotes, right? The number of asymptotes is 3 because there are no finite zeros. Okay, so 3 asymptotes. One is going to be along the negative real axis. The other one, with the 3 asymptotes, you see it's going to be 180 over 3, so it's plus and minus 60 degrees. So, and then you find the origin of the asymptote is going to be somewhere in here. Okay, and then you find the breakaway point, the dk/ds thing that you go through. You start out with the characteristic equation, solve for k, then do the dk/ds equal to 0. That gives you your breakaway point in this case. Okay, and so it's pretty much, you know where k equals 0, you know where k is infinite. It's at the ends of those asymptotes. Okay, over here you have 3 poles and no finite zeros. Again, you've got 3 asymptotes. And the root locus exists to the left of that pole there, and it goes on, that branch goes along towards minus infinity. And the 2 asymptotes are going to have angles of 60 degrees, right? And so, and you know that the branches of the root locus approach those asymptotes. This case here, that you have a very symmetrical case, and it turns out that again, you can determine where the root locus exists on the real axis there and between there and there, right? And then, there are 2 poles here. The root locus, the branches of the root locus begin branches begin at the open loop transfer function poles here and here, start moving in. They also start here, 2 branches start here and move in. away from the open loop transfer function poles towards the open loop transfer function zeros. In this case, the asymptotes will be the same as the branches of the root locus. Okay, it's so very symmetrical. Remember, when you have something like this, a pole there and a pole there, it's symmetrical. Okay, and so what the root locus looks like is this, right? It breaks away, one goes up, one goes down. I mean, the root locus itself is symmetrical, and the poles and zeros, there's only poles in this case, are arranged in a rather symmetrical fashion. I mean, so that this is a case of 4 poles. This is a case of 2 poles there. Right?
Is there a way to tell when it's going to exist on the asymptote?
You apply the angle condition. Right, it's easy to apply here, okay? Right, let's take a test point there. You draw a vector, remember, draw a vector from each of the poles and zeros to that test point. So you take a test point there, draw a vector from here to there, vector from here to here, a vector from here to that test point, vector from here to that test point. And so you can see that these angles here is isosceles triangle, okay? And so this angle in here will be the same as this angle here, okay? And also, this angle is at minus 90, this angle is plus 90, right? So in that case, what you have is a sum of there are no finite zeros, right? So you have this the sum of the finite zeros minus the sum of the finite pole angles. We're talking about angles, right? So you've got a theta, which is, say, that angle there, and the other one is 180 minus theta, right? That's going to be this angle here, measured relative to the positive real axis, okay? And then you've got minus 90 and plus 90. Minus 90 plus 90. So these cancel out, and the question is, does that equal to 180n? That's the angle condition, right? So, and so this is actually the sum of the zero angles minus the sum of the pole angles is equal to 180. Is this true, right? Question mark. Is the left equal to the right? And it is true, right? Because the left-hand side will be equal to this cancels with that, this cancels with that, minus 180 is equal to 180n for n equals minus 1. Okay, so that proves that any point here and consequently any point below lies any point here. They're complex conjugate, right? So similarly, you can take other. Well, we know the root locus exists on the real axis because of the. Basically, it comes down to the angle condition, but it exists to the left of an odd number of singularities, right? And then we can take a test point here as well, or here, right? And we can use a similar argument of one angle is going to be the complement of the other angle, that kind of thing. I'll let you go ahead and show the MATLAB that I have. Yeah.
You said to the left of odd number of singularities.
Yeah.
I'm guessing you don't count the ones that are in the air.
Yeah, you don't count the ones that are off the axis, but even if you did count those, one would cancel with the other.
Oh, okay. Got it.
Let me show the MATLAB. So this is define the numerator, define the denominator. This is a SS plus 2, S plus 3, right? In other words, if you have a system that looks like this, K over S, S plus 2, S plus 3. Then your H is 1, this is your G, and you can multiply this out, right? And you get S cubed plus 5 S squared plus 6S. So your coefficients are 1, 5, 6, and 0. S to the 0, this S to the first pack. Okay, so that's the first system there, and so you can execute this. I have several. We don't have to go through every single one, but this will execute in a second. So we can take a look at those. Where is it?
What is n equals 1, Professor?
N equals 1 is the numerator. The numerator, in other words, was, this is 1 times K. K is kind of in the system is going to go from 0 to infinity. Okay, so the numerator, you can say numerator is equal to 0, 0, 0, 1 like that, or you could simply say n equals 1. Right? This is 0s cubed plus 0s squared plus 0s plus 1. And in the denominator we have 1, 5, 6, and 0. Okay. And so that's the reluctance. And then on the reluctance you could do things like first enlarge it, and then you can click right there, and that the gain K, the gain K for stability is going to be less than 30, and the pole at that point is at square root of 6 is 2.44 J, right? And the complex conjugate down here, and then see K equals 0 here, K equals 0 here, and you throw in your asymptotes. You can find the gain K also when you can find the pole when the gain K is equal to 30. That's actually exactly, it should be ideally 30. And so over here you can go along until K equals 30. And you find the pole is at -5. Okay. And you can print this out or whatever. And go to the next one. The next one has enlarge it. The next one has 3 poles, right? And no finite zeros. And so it will have 3 asymptotes. And so the angles will be plus or minus 60 degrees and 180, right? And one asymptote going out that way. And this branch lies right on that asymptote, right? So, so this one, notice that it doesn't have any entry points to the real axis, right? Doesn't have any entry points. In other words, if you try that dk ds equal to 0, you get a complex number, and that doesn't. But when you do the dk ds equal to 0, that's to find the point at which the gain k is a relative minimum or maximum, and that's a breakaway or reentry point. So there is no entry to the real axis because you have the three asymptotes here, okay? This asymptote here towards that zero at minus infinity, this asymptote, it'll have an origin and an angle of the asymptote. The angle is going to be 60 degrees. All we have to do is find the origin of the asymptote. And then here, like for example, what was it? Sum of the pole angles minus the pole locations. We have pole at -1 plus J1. And then we have -1 minus J1. Notice that the imaginary components cancel out. So it's the pole location, so we have a pole at -1, right? -1 equals 0. But it's good, I guess, if there's partly lit up, right? Oh, okay. Did you fall asleep?
No.
And so we get, this gives us minus, what am I trying to find here?
Minus -1.
It's the location of the.
They're all poles.
The start of the asymptote.
See.
It's -3.
It's, you're finding the,
-1, -1.
they're all poles.
And it's, so it's it's not equal to 0, right?
It's the origin signal.
You divide by 3, right? So it's a -1, right? So the origin of the asymptote is right there, right? So this asymptote goes up that way, this one goes down that way. And again, you can find the range of gain k for stability, right? And in this case, gain k is about 9 point whatever. And the pole, notice that they don't give you exactly, it doesn't give you exactly the the real component of 0. It gives it very small. I can't adjust it that closely.
Probably 9.5. Probably 9.5.
9.5 probably, and the pole, and then it's probably J2. Like that. That's the one we looked at that, right?
Mhm.
And by the way, you can find the range of gain k for stability, which is actually 2. The gain k has to be less than 5 or so, and for stability, for all the poles to be in the left half plane. And see, for a given value of gain k, we can find the poles. If you have the root locus, and no, if the gain k is 5, we can also look over here and see what's going to happen is that. These will come together, right? We were saying it before. These two branches come together. These two branches come together, and then they break away. One will go up this way, the other will go down that way, the other will go that way, and the other will go that way. Okay. See, in other words, let's take a point there. Again, k is about 1, right? It's about 1. And then here, we can find where the gain k is also 1. And here, actually, 1, okay. So we can find the pole location when the gain k is equal to 1. We should have 5 poles. How many poles? 4, right. Closed loop transfer function poles. That's what this shows. Closed loop transfer function poles, right? As the gain k increases, see, what does this one do here? What does it do? We can find where the locus exists on the real axis, right? There's a pole there, a pole there, a pole there, and a pole there. And it's not quite as symmetrical as the previous one, right? The previous one was kind of like a square or diamond. So the root locus exists here. And we can find, let me see, there are 1, 2, 3, 4. There are 4 asymptotes, right? No finite zeros. We can find the origin and the angles of the asymptotes, right? There's going to be 1 origin and 4 angles, right? And let's say that it probably is going to be right about here, the origin. So we have that angle there, and then up that way. Maybe it's about here. So up that way, down that way, down that way, and up that way. Yeah, this is one possible root locus for this arrangement of poles and zeros. Sometimes, if you notice that when we did have the more diamond shape, the root locus passed right through the asymptotes. Okay. Let me see another one there. Remember, just keep in mind that there are 4 poles, no finite zeros here. There are 2 complex conjugate and 2 real, 1 at the origin. Okay, go to the next one. Very similar. In fact, I can put both of them up on that. This one has the poles at -1 plus or minus, looks like J1, and pole at looks like -3 or so. This one is at -5. So they basically look the same. The arrangement is much the same. There's a breakaway. Oh, are they the same?
Are they not? 1 extra pole.
Oh, this one has 3 pole, an extra pole, right? So yeah, they're not the same. But you can find where the root locus exists on the real axis here and there.
It's just got an extra asymptote.
Pardon?
It's just got an extra asymptote.
Yeah, it has an extra asymptote because it has 5 poles, right? They have that pole, there's one asymptote here, that one doesn't have it. Okay. this is figure 6, that was figure 5 there. And notice that this has 3 poles, 3 real poles, 2 complex poles. This has 3 real poles, 2 complex poles. And so it really depends on the locations of those poles and zeros. You're not always going to get the same shape, what do you call it, same shape. It's not going to duplicate for different locations of those complex poles and real poles. Because this one, you see these 2 poles, it starts here and then it goes off. And here, off into the left half plane. Here, starts there, goes off into the right half plane. Okay. So the thing is to be able to not every time draw the exact root locus, but to draw something that's reasonable. It sounds reasonable. Or looks reasonable. And this is one that we have already seen before. Right? This one has a pole at the origin, a pole at the 1, and a 0 at -2. And so if you didn't have that 0 there, you would only have these 2 poles. And if you have only those 2 poles, what does the root locus look like?
Up and down, and we go here and then.
Yeah, the 2 branches move towards each other, then they break away in the middle, right? So you wouldn't have that. You'd have basically you'd have a cross, right? And you have an unstable system because the poles, the closed loop transfer function poles, will always be in the right half plane. And then what we did, we introduced that 0 there, which really what we did was we introduced PD compensation. Right, proportional plus derivative compensation. We put in an S+1 factor in the new S+2 factor in the numerator, right? And what happened was that the root locus was attracted by that 0 there, and so thus you're able to stabilize the system using PD compensation.
Okay, that's what I was asking you. You're adding things in the system to just drag that towards the left,
You're
right?
reshaping the root locus, okay? You're reshaping it to satisfy specifications. It's to first stabilize it, and then you'd like to place those poles, the closed loop transfer function pole, to satisfy a settling time specification, a percent overshoot specification, okay? And that's what we're going to get into starting next time, is design, using lead and lag, possibly a combination of lead and lag, but I probably will just do lead compensation and lag compensation separately, so as not to introduce too much complication. We just have those 2 using using the root locus, using root locus, design using root locus, okay? And then after we do that, we'll go into the next chapter and we'll start on Bode diagrams, and then eventually use Bode diagrams, in other words, the frequency response plots, to design our compensators, lead and lag compensators. So that's where we're going in the next, next few times. Any questions? So try to practice with these root locus plots. Maybe you could do some root locus with MATLAB to kind of give you a check on what you came out with. You can compare it with MATLAB. I can put these particular MATLAB code on the web forces